Okay, wonderful. So, welcome to day 5, everybody. And thank you so much for making it. I know it could be challenging to make 5 days in a row, but I think most of you you did, and congratulations, well done. So today we are talking about a very important topic, which is about evaluating the performance of models. Okay, let me open my RStudio. Please let me know if you can see my RStudio.
Yes, we can.
Yeah, we can see.
Okay, so let me start with a simple example, just to, again, recap and also tell you what we are going to do. So I start by bringing my FPP3 package, and I'm going to use the tourism data. So instead of actually looking at the tourism as it is, where we have many time series, I'm going to focus on one time series. But actually, whatever we do with one time series, we just replicate the same thing with other time series. So whatever I do with one time series could be done with many time series as well in Fable. So I want to focus on the tourism in Australia rather than tourism by region, state, and purpose. So total trips in Australia. So to do that, I go and index by quarter and then summarize. And then I want to go and take the trips, and I say the trip should be the sum of the trips because I group by just this column, which is the quarter. And I call this Ask for Australia Tourism. And then I run, and I will get now one testable. It's a quarterly time series testable. I have quarter, which is index, and trips is a measurement. So there is no key here in this one. All right. So I don't, of course, do the data preparation visualization. So I skip those steps. Now I go to the modeling part. So I want to apply the models we have covered so far in this time series and produce a forecast. So to do that, first, I pass my testable using a pipe operator to the model function. Inside the model function, I specify the list of models. I start with mean, and then I go with the other models, naive. So I want to make sure the names actually are correct, because remember, functions in Fable, I mean, when we talk about functions, I'm talking about forecasting models. So the functions that correspond to forecasting models are in capital letters. You need to remember that. So this is my second method. The third method I want to specify is seasonal naive. I put a comma. We had also regression, which is TSLM. This is the function for time series linear model, or simply it's just regression. Here, this is my response. I provide two specific functions, trend and season. So you know how this works now, right? This is just a linear trend, and the season is creating dummy variables. And because I have quarterly, I will have 4 seasonal indices, each for quarter. The next model is exponential smoothing. The function for this is ETS. And I just provide a response variable. Or maybe actually I call this automatic ETS. So this follows the algorithm we discussed yesterday. And actually, I recommend you to do it, except in some circumstances, you may go and provide those specific functions using tilde, like error plus trend plus season, right? So, and then of course, inside this, you need to provide whether error is additive, multiplicative, whether trend is additive or additive damped, and whether seasonality is additive or multiplicative. So with these letters. So if you want, you can do it. And this sometimes is helpful to understand the ETS models, but you don't really need to do it because this algorithm is very powerful, especially for monthly, quarterly data is reliable. And of course, I can also have automatic ARIMA. So I provide the function for ARIMA, and then I put the variable I want to forecast, which is this column here. All right, so I give a name to this. The name could be anything, but you can always put a name that is meaningful. So I run this code, and then I can go and then look at my model table or Mabel. I have 1, 2, 3, 4, 5, and 6 columns. That is because I have 6 models here. What is next? Well, the next is I want to produce a forecast. So I take my model table and I pass it to forecast function. So inside this, I have to provide how many periods I want to forecast for. And I give this a name as well. Now, if you use regression, because the other models that we have here, this tree and ETS and ARIMA, they don't take into account predictors or regressors like population strike and other things, but TSLM does. So if that is the case, you cannot just provide H equal 4. So you have to do new data equal, and then, I don't know, provide a data set for this, okay, that has the future values of the predictors. Okay, so if you have predictors, you need to remember that. And in the apply exercise with the vaccine data, you do something like this. So you go through it really in detail, and there is actually a bit of work to do there to prepare that test data. Here, I don't have any predictor, so I just provide H equal 4 that corresponds to the 4 quarters ahead. And if I run this, I get my forecast table, which has that model containing the list of the models that I have here, and then index the variable I want to forecast, and then the point, the forecast and its distribution. So here, as I said, we have only normal distribution with a mean and a variance. If you want to use other ways of producing probabilistic forecasts, not assuming residuals are following normal distribution, then you have used bootstrapping, and it is where you just go and put boot equal true. And this will now do the job. So it wouldn't rely on normal distribution assumption. Okay, so I fit the models, I produce the forecast. And of course, you remember between this, you can do a lot of things. You can go and look at the report, the components. If you are interested in understanding the fitting, the residuals, there are a lot that you can do between this, right? Using glance, tidy. So again, these are the functions that you have used before, but I just typed them here for you to remember. So glance, tidy, report, components. There is another one called augment. These are the functions that you need to remember if you are interested in understanding the fitting. Okay. So note them somewhere, and then if you want, you can use them. Okay, so now I have my forecast. What can I do next? Well, I can produce a forecast and then visualize it if you like. And then visualization, as we did it yesterday, could be, you can visualize anything really: point forecast, prediction interval, and then distribution. So I will probably do the distribution one with ggplot. So in ggplot, I say the data that I want to actually use for this is this forecast that has my forecast information. So that's one thing. And then I need to provide what we call mapping. Again, if you're not familiar with this, these are all from ggplot2, so in tidyverse. So you need to go and learn ggplot2. So when it comes to mapping, I need to provide different elements of a plot. So I want to say how I want to map the columns on this in this fable, which is FCT, in this object, into the different elements of a plot. So that's why I say mapping, aesthetic, and then here there are different types of aesthetic. Two of them, they are X and Y. In this case, because I want to produce a distribution, I use ydist. And actually, because I'm going to use ydist, I need a new library to use here called library ggdist. Now, just to have all my libraries at the beginning, I will go and put this here. Okay, so if I just run that as it is, well, it doesn't actually do anything. So this is my data mapping aesthetics. So I actually have to say, again, remember I'm using this data. So X is quarter, let's say, and then my distribution is this one. So if I run this now, I just get this blank surface here. So if I want to add something to this, I use the plus, and then there is a function that I want to use here that corresponds to what I want, which is this one. This is a function from ggdist, as you can see. And then if I run this now, I will get a distribution of whatever I forecasted. Now the problem is, you can see there are many of them. So each one is corresponding to one method. So as you can see, actually the forecast they produce is quite different, right? I don't know if I can do something like this. Fill equal. So what if I give different colors to different model? Let me see if it can do that. Oh yeah, it does it as well, which is nice to see. Let me see if factor whether one more parenthesis here. So there is one option called alpha. Let me see if that alpha works here. Yeah, alpha is transparency, so you can have you can see if the distributions overlap. So this is interesting because you see actually how the distribution of the forecast generated by these methods varies for the 4 quarters we produce the forecast. For instance, the average, as you can see, it is quite in the bottom of this y-axis, but the others like automatic ARIMA and ETS, they are in actually the higher side. So they produce higher values of the forecast variable, and they are also less dispersed. So if you look at the average, so it is not narrow, the distribution is wide. So it means there are more variance there more variability in the forecast they generate. So you can do that if you like, but we could also go and focus on just one method. So we can go and say filter, for instance, I will just produce this one. So that model, I think I put it automatic ETS, just let's say is automatic ETS, right? And if I do that, then I just say my FCST ETS. And then this time I will use this data. And actually there is no field there, but anyway, it is fine. So now I focus on the only exponential smoothing, and you see that how it actually changes from Q1 to Q2, Q3, and then Q4. The point is the point forecast, is the dot mean that we see, right, in each period. And then this is really important. So again, if you are new to this, like distributions, if you haven't used them before, I think you can also invest some time to understand what is a distribution, how I can extract the different elements of a distribution. So this is the point forecast. If I want to extract prediction intervals from this, then I can do it as well. Then the prediction intervals would be that interval. And then, of course, the area under this curve corresponds to a probability. Whatever probability is that, it could be whatever coverage you want in prediction interval, 90%, 95%, whatever. So in this case, you will get two values for the prediction intervals, right? You will get this value here, and then this value there. Okay, so if I want to draw it here, so I have the distribution. From the distribution, I get my point forecast, but I get also an interval, right? And then I can also go and get what we call the quantile. Okay, so a quantile, for instance, I will show it in this distribution. So a quantile is something like this. So again, you have a line that corresponds to a point here. Remember, the y-axis is the value of the forecast. So this quantile also corresponds to this area. Okay, so again, you can go for 90%, 95%, whatever quantile. So when you determine that value, and I think there was a very good question yesterday or day before about how we determine that coverage, and my answer was that 90-95%, it depends on your business that you manage. Well, typically in a statistic, we look at the 80, 90, 95%, sometimes even 99%, but you need to understand what is the value that corresponds to the service level in your business. So you determine that, and that quantile will give you also one value. Okay, so again, the quantile is going to be a value, but when you say a quantile, it means that value with that coverage or percentage of or the quantile, it means everything else would be below that, right? So if you want, you can use this distribution to manage the risk in your business. So you say, let's say, if this is the demand, for instance, if this is a distribution of the demand, I want in my business to satisfy up to 95% business demand that comes to my business, and I'm happy to take a risk of 5%. So if if there is more demand and I cannot satisfy, I will take that risk. It's fine. Maybe I lose the customer, or maybe I sell less, or it will show up in my profit later. It is okay. I take that risk. So if that's what you're looking for, you say, okay, I will go and take the quantile of 95. That will give me one number, and that number corresponds to what we see here, and that would be your quantile number. And this area here would be the risk that you take. So it means in this case, you set up your system in a way that can handle any demand up to this. Okay, anything more or less, it is and actually this is the other way around. I should show you the other way, because this is the lower side. I always tend to consider this as the lower, the higher values, but in our case is not actually in this example. And you can, I think, maybe reorder this as well. But in my case, that's what I wanted to show you is this side, because these are the higher values. So if I take a 95% quantile, it would be something like this. There. That will correspond to a value here, whatever that value is. And then that means you set up your system that satisfies the demand up to, I don't know, 29,500. And then you take the risk. If there is anything more than that, which is the probability, there is a low probability that demand would be high in this quarter, but you take that risk. So what I want to highlight here is important to understand what is a point forecast, what is a prediction interval, what is a quantile, what is the entire distribution, because we are actually going to go and evaluate the performance of each of the elements that I discuss here. Okay, let me clean this a little bit. Okay, now let me do one more thing. Well, I could, I think, add also the data that I have used here. Maybe with an auto layer. And then I think I could just look at, I can do it with filter index. I use filter index just to show you again how we use filter index. So filter index goes and filters the index part of my tessable. If I look at the tail of this, okay, so it is maybe, I say from 2017 of Q1 until the end. So that point means end. So if I do that now, I can, maybe I will actually do that one. All right. So now you have the actuals and then the distribution that you produce. Okay. My idea was to get this data, the fitted values, and also the prediction, the distribution and prediction interval and everything here. Okay. So I wanted to get a distribution here as well, like what we saw before. I have never done it before, so it seems like it couldn't be just done with what we had, like the code. So that's what we do in forecasting, right? Basically, this is, I recap this just to start really this discussion now. So the one that we see in red here, this is my actual data. The green one is the fitted value. And then I could, maybe I will use a different color for this. And then I have what we call the forecast that I produce for the future. All right. So we did all this modeling for these two main purposes. One, to produce the forecast for the future, and then also to get these fitted values. Now, what we are interested in is how well these models, like we had in the list, they do. Actually, what do you mean by this? Well, there are two aspects that we need to think about here. All right. So let me repeat this. Here we have a list of models. So for each model that we apply, we can get a fitted line that we see here in the green, And then we get also the forecast as a form of a distribution, but also point forecast and prediction intervals and quantiles, if you like. So now what we are interested in is knowing how well these methods or models do. There are two different aspects to this. How well these models fit the data and how well the models produce the forecast, how accurately the forecasts are, how close those forecasts are to the real values. So these are two important things, two important concepts that we cover today. All right. Now, you may tell me, why don't we just use the fitted values? What is wrong with getting a model that goes and fits the actual data completely, 100%, 100% fit? Any idea, anyone, why this might not be a good idea? Okay. So if you could put something in the chat, it would be nice to see what you think. So what happens if I just rely on only a fit? So if I draw something here, what happens if I just go and follow the actuals? And this is possible, by the way. You can always get 100% fit. What is the issue with this? Any thought on this? That would lead to overfitting. Wonderful. Overfitting. Can you tell us what overfitting is? So the problem is, if I rely on a model that gives me 100% fit, I will have an issue called overfitting. So what overfitting is? Any idea, everybody? At least, yeah, we are making point forecast and we lose the probability of being other points. Overfitting affects generalization. But what is overfitting? Tendency of a model to fit well in the training data, but poorly when it comes to forecasting. A very good answer. Okay, so let me tell you why actually in forecasting there are two things they are not good. So imagine if you have a data like this, and then you get a model, and this model produce a fit like that. Okay, so this is a fitting created by a model. Total average, or the average or mean method that we use, does something like that. Why this is bad? Why having a model that fits the data like the yellow line, I mean in this example, is bad? What do you mean by underfitting? So Edson said this is bad because it underfits. What do you mean by actual data? Because the other one captures the actual data, actually. If it is overfit, 100% fit, it captures actual data. Yeah, absolutely. Actually, what this fails is capturing the underlying pattern or systematic pattern or signal that or association or relationship that we have discussed so far. So this yellow line fails to do that. Okay, this is bad in forecasting. The overfitting one is bad as well because it goes through every single point. So let me very briefly talk about this, and then we can, I think, move on to talk about accuracy and how we evaluate it. So every single observation in forecasting and machine learning, and this is basically the same everywhere. So everything that we do, let's call them Y. And in our time series forecasting, this could be basically YT. So this YT has two components. And I use something like a plus just to tell you this component plus that component. So everything that you observe, the production in Australia of beer, of bricks, the demand of vaccines in any country in each month. So here we talk about time series, so we have the index as well. So we talk about the measurement of each month. So the consumption of doses of vaccines in each month, let's say in Kenya, for instance. So this has two components. What is the first component in your opinion? So everything that we observe or we record in the historical data, it has two components. The first component and the second component. I will start maybe by the second component. The second component is something that we call it irreducible error. Okay, so this is irreducible error. Well, this part is what we call systematic information, or that underlying pattern that you mentioned, systematic information. Okay, so everything that you observe has these two elements, some systematic information and some irreducible error. So this irreducible error, again, is something you may call it randomness. Okay, now what irreducible error is something that we can't do anything about. Regardless of what method that you use, you're going to have that. And it's a part of actually the actual observations, the actual data. So in everything that you observe, you have that. What is systematic information? Well, actually, this is the patterns that we have discussed so far. So here, typically we use x1, x2, up to any x. What is x here? Is that pattern. It could be a predictor, like population, like a strike. It could be dummy variables. It could be systematic information by seasonality or trend, etc. So the idea is to see how those systematic information could be related to the variable we want to forecast, and this is through this function. So basically in forecasting, we have different methods: ETS, ARIMA, regression, naive, etc. Each model tries to get an estimation of this fx. So one method is f hat x, another one is f hat 2x, etc. So each method is trying to capture this relationship because we cannot do anything about this. So this is something, let's say, like that. If I make it, we cannot do anything about that. However, we can do this one. Now the question is how well we can do this one. So I'm going back to the problem of overfitting. So when we talk about overfitting, If we try to match every single observations that we had in the past, it means not only we went and maybe hopefully identify systematic information, but also followed that irreducible error. So, and this is not good because we cannot do anything about this. And this is related to a topic in forecasting and machine learning called a trade-off between bias and variance. Okay, so this concept is quite important in machine learning and forecasting. So what is bias? Well, you can say actually bias is how close the estimation or fitted value to the actual. What is variance? The variance is how sensible your model is to a new data. So if you get a very low bias, which is the case of overfitting here, because we go and every single observation would be close to the actual, we get a very large variance. Okay, the thing is, if you go and have a line like this, maybe variance is lower, but bias is very high because those points are very far from that. So in machine learning and forecasting, we try to have a balance between these two. And this is also related to the concept of overfitting. Okay, so we want to balance these two. We don't want to be, 100% match the actuals because we know that there is an irreducible part in each observation. We just want to get the systematic information. And that is why we prefer a method like what we see here than the method that goes into every single point and fit it 100%. Because we know that the variance of that method would be very high. It would be very sensible to new data. So we don't want that. So that's why we don't just rely on a fitting only. We want also to see how model performs on the new data. And this is the idea of looking at the accuracy. Okay, now let me go to my slides. Not this one. This is for yesterday. If not, I have to go and open them. So let me go and open it. All right, so to summarize what we said, so when we train models on the data, we get the fitted values, we can extract it with the augment, and then following that, we produce the forecast.
We are not seeing the screen.
Yeah, I'm not sharing the screen. I'm looking for my slides. Just 1 second. I will open it. So we produce the forecast for the future. Now the idea is how to evaluate that. And actually, before doing this, let me show you something here, maybe in Excel. Yeah, I want to show you this example in Excel. And I want to discuss different concepts that we have covered here. Maybe they are not clear. We make it clear here. Let's assume we have this quarterly data, which is up to the quarterly 3 of 2023. I just deliberately make it real time for you to understand the concept. And this is the data. And you know that this is a testable, right? This is index, this is the measurement. It's one time series only. And now let's assume we have a forecasting method called naive. And we know how naive works. To estimate one period, we look at what we had in the previous period. And if you want to forecast for many periods in the future, we just repeat that. All right. So let's assume we have this. And then now I'm trying to explain the model part in Fable and also to forecast part. So I'm going to apply naive because it's simple. Let's call this column the forecast. So if I apply naive to this, what would be the estimation for this period here? Or the forecast for this period using naive? Well, the forecast for this period is what I observed in the previous period, but there is no previous period. So that's why you see NA in Fable later. Now I go to the next period and I say, what is the estimation for this period? Well, it is what I observed in the previous period, which is this value. What is the estimation or the forecast for this period? It is what I observed here in the previous one. And actually, you can keep doing this up to here. Right? So if you check that, you see that the estimation for Q3 of 2023 is what I observed in 120 in the Q2. Now, what if I want to forecast for future? Let's say for this 4th quarter. Well, I can also go and say the forecast for this would be what I observe here. But if I want to forecast for this period, Naive tells me, look at the previous one, but there is no previous one. And that's why I just repeat basically what we had before. And that would be the forecast. Now, I want you to distinguish few things here. This is the data I used, right? Let me use a different color for this. And these are my forecasts as well. Okay, so this is the data I use. These are my actuals. What is the name for this? Any idea what the name we give to this? What is the terminology that we use for this? This is what we call fitted values. Okay, so fitted values are generally one step ahead forecast. There is an answer here. To see fitted values. Yeah, well done. All right, so this is what we call fitted values. What about this 4 that we have here? What is the name we give to this? Forecast. So these 4 values are the forecasts. These are fitted values. Fitted values are typically one step ahead forecast, as I did now. If you go back to, what I did, you remember? In each step, I forecast for the next one. In each step, I forecast for the next one. Each step, I forecast for next one. I keep doing that. And then at the end, I produce the forecast for any future that I have. So I call this forecast, I call this fitted values. Now, I can go and do something. I go and calculate the difference between these two. What is the name that we have for this? Okay, not error, no. The error is actually not the right terminology here, and that's exactly why I wanted to clarify this. Soda, I don't know if I pronounce your name correctly, but I think you mentioned it, and Elias mentioned it as well, Jacinta as well. So this is residuals. Okay, so the residuals are the difference between the fitted values and the observations. What about this? Well, imagine I'm at the end of quarter 2024. Cool. I imagine I'm in the end of that quarter. So, and then for that, I created, of course, the forecast. And then after that, I will get also the actual by the end of that. And now I can also calculate the difference. What is the name for this? Error? Any other ideas? Forecast error, yeah, I think it's better. Forecast error, not forecasted residuals, no. You can use error or forecast error, okay? So we call the forecast error. So I want you really to distinguish all these things, all right? This is what we called residuals, fitted values. This is what we called residuals. This is what we call forecast. This is what we call forecast error. And you need also to remember, fitted values are typically one step ahead forecast, but forecasts are generally multiple steps ahead. They could be one step ahead as well. Okay. So now, this concept are important because residuals, they help us to evaluate the performance of the model, but they don't tell us how accurate the forecast is. They are useful in terms of telling us whether any information is left in the data, I mean in the residuals here, okay? So we use residuals to evaluate the performance of the models. How? We look at them and we want to see whether any systematic information is left in residuals. But residuals, they do not tell us anything about the forecast accuracy. The forecast accuracy that we see here must be calculated only based on the new data, right? Because I use this data up to here, and I forecast from here for this 4. So my model didn't see any data after this. So this is the new data to my model. And I use this to evaluate the forecast accuracy, which is the errors here. And then I can now calculate the forecast accuracy. So remember this, and then we will come back to another important topic with this example later. Now, let me do one more experiment and then tell you what you think. Now, to evaluate the forecast accuracy, so what we said here is, we say we produce the forecast, we wait for 1 year, 4 quarters, we get it, and then we calculate the errors. What would be the issue with this, to wait 1 year? Well, the issue is maybe I have to make a decision now, right? I don't want to wait. I have to make a decision now because I need to forecast for those 4 periods to inform a decision. So in that case, what should I do? Well, that's where we do a basic forecast accuracy evaluation. We say, because I want to forecast for 4 periods, I will come to my actual data and I say 1, 2, 3, and 4. Okay, so I have 4 periods. I pretend I don't know anything about this. Not sure how to get rid of this. Maybe with black. Okay, so I pretend I don't know. And this is what we call now a test set. So I have a test, and this period I call it train. Okay, so train, and then test. So this is a simple train and test split. Or sometimes we call this in sample. And then we call this out of sample. Okay, so now we repeat what we did before. I just go to the beginning, I calculate the fitted values, and then residuals, and then I produce the forecast for this. And then now I reveal those actual values, and I can calculate the forecast error. right? And this is what happens. So when you want to forecast for the future, you don't have the value of real future. So what you have to do to evaluate forecast accuracy, you pretend you don't know a part of your data, you fit a model and the train, and then you evaluate on the tested. The simple approach that we start with is a simple split between train and test. There is a more advanced one that I will introduce it later. Well, the approach that I discuss here is the test set is equal to the forecast horizon. Okay, the simple split of train and test. If my forecast horizon is 4 period, I will come and I will hide 4 last periods. I'm still talking about the basic approach. There is more advanced approach where I explain later. Okay, so the split is like that. If you forecast for 12 months, well, you have to go to your data. If your data is monthly, and then you pretend you don't know the last 12 months. Okay, so these concepts are very important to understand, and this helps us to see actually how we have to calculate the errors. So now let me go through this very quickly, and then we can continue after the break. Okay, so here we introduce the concept of basic training and test, what I just explained, and then we move on to something more advanced. So we want to evaluate forecast accuracy. And then I will show you how to evaluate forecast accuracy for the point and then also for the distribution, which includes the prediction interval. Well, if you want to evaluate how good the model that you use is for the forecasting, we have to compute its accuracy. And the accuracy is between different models is compared by measuring errors, the forecast errors. And this should be based on a test set. And the test set is a set of data that is new to the model. It means the model hasn't used it. Now, there is an important concept, and we don't talk about it at all, but you could investigate a bit more later. Ideally, the forecast performance should be evaluated based on the benefit the forecast provides to your business, not simply because of the accuracy, because there are different aspects of the forecasting that you may consider. One of them is the accuracy based on the errors, but there are other aspects of forecasting quality that you may consider, including the business impact or the decision impact. So ideally, you should be choosing a forecasting model that leads to the better business decision. So surprisingly, the association between forecast accuracy and decision impact is not linear. It doesn't mean that if a model gives you the most accurate forecast, the decision impact would be also best for that model. So the association is not linear, right? So, but ideally, this is what actually we care about. So if I care about a model that gives me a good staffing cost, least CO2 emission, high service level in my replenishment, less stock out, less inventory cost, fastest response. These are what I care about at the end. These are the performance measurement for my business. So I need my forecast to contribute to that. But actually, this is not quite easy in many cases to calculate or understand. So that's why we don't talk about it here, but I want you to have it in your mind that forecast accuracy should lead to something that business cares about. So what we do here is we focus only on the forecast accuracy error metrics. So that's why we split the data into train and test. And then we want to evaluate the forecast accuracy on the test set. And we just covered why fitting, it could be a good thing to look at, but the fitting and residuals are not a reliable indication of forecast accuracy because of the bias and variance trade-off. So a model which fits the training data very well, that doesn't necessarily forecast well. This is very important to keep in mind. And we can always get a perfect fit, as I highlighted, with increasing number of parameters. And so overfitting a model is bad, and failing to identify systematic information is bad as well. You want something between. So to do that, we mimic the real life situation. So we, as I said, pretend we don't know one part of the data. We fit the model on the training or in sample, and we evaluate the accuracy on the test set. And basically, this is a simple time series, and this is how we split the train and the test, similar to what I show you in Excel. So now let's see how we evaluate the point forecast accuracy. So to evaluate the point forecast accuracy, we first calculate the errors. That's what we did in Excel as well. So the difference between the actuals in the test set and then what we forecasted for the test set. This is the first thing we need to do. We calculate the forecast error. And then, because we have these errors for different periods, depending on the horizon, we can go and calculate different error measures, right? So this is what we call measures of forecast accuracy, error metrics, or accuracy measures. This is the error that we calculate for different periods. Each error measure for the point forecast accuracy, they go and they take the error and they summarize it somehow. So this is mean absolute error. It takes the error and it goes and takes the average of the absolute errors. The mean square error, it takes the errors, square them, and then take an average. If you are interested in the root mean square error, you take the square root of it. And then you can also have an scale independent, like mean absolute percentage error, where you take the error, the absolute value of it, divided by the absolute value of the actual, and you multiply it by, you take the mean and multiply it by 100. Now, you may need to distinguish between a scale dependent from a scale independent measure. So when you have data set in different scales, let's say you have many time series, one of them is a scale of 1 to 5, another one is a scale of 10,000 to 100,000. This is how they change. You need to use a scale independent measure. Otherwise, your forecast error depends on the scale of your data, and it's not a fair comparison. So you have to use a scale independent measure if this is the case. If you forecast only one time series, or you don't have the scale issues, then you can rely on mean absolute error and then root mean square error. Of course, there are many other accuracy measures like mean absolute scale error. This is actually something that you could use instead of MAPE. MAPE is the accuracy measure that is not recommended to use. There are issues actually with MAPE, including if you have low volume data or you have zeros in your time series, even if 1, you cannot use MAPE because it is divided by 0. But it also penalizes the overestimating and underestimating differently. So we can use MACE instead of MAPE, if you like. So MACE is something like mean absolute error, but scaled based on fitted values of naive in sample data. So that's what we see basically in the queue. And then if you have seasonal data, in that queue, you can use the seasonal naive. And the scale of this is, it could be equal 1, greater than 1, and smaller than 1. But this is not really interpretable. So equal 1 or smaller than 1 and bigger than 1 doesn't mean that the method that you're investigating is better than naive or seasonal naive. Okay? Sometimes people can, misuse this MACE, so don't do that. Just use it as a score to compare the accuracy of different methods. We have also the scaled measure of the root mean square error, RMSSE. This is also available in Fable package that you can use. Okay, so what if I want to evaluate the distributions of forecast accuracy? Well, first we talk about the intervals. So in the interval, we have prediction interval. And again, you remember in prediction interval, I have a lower bound and upper bound. Okay, so I have the point forecast, I have high and low. So this is the bound that I'm talking about. So if I ask you as a decision maker, are you interested in a prediction interval that is narrow or wide? What would be your answer? So if you are a decision maker, are you interested in the narrow intervals or wide intervals? Narrow interval. Any other ideas? Narrow. Yeah, of course, because if you want to, let's say, make a decision based on the estimation of the demand, and if I tell you the demand changes between 10 and 10,000, it's not really helpful. But if I tell you, well, the demand changes between 1,000 and 1,200, it is much more informative, and you can balance your risk based on that. So width of the interval is important, and this is what you see here. But sometimes when you produce the forecast, the actuals could be within the interval, but sometimes could be outside the interval as well, right? So you may have this, you may produce this prediction interval for one period. Sometimes you may have actuals, they are inside. If that is the case, we are here. It means the actual is between the lower bound and upper bound. And if that is the case, the score we calculate is simply the width, the difference between upper bound and lower bound. However, sometimes the actual might lay outside of upper bound or outside of the lower bound. If that is the case, the score we calculate is not only the width, that is this, but also a penalty for this and that they lay outside the interval. And this is what we see here. Okay, so we have the interval, but we add a penalty depending on whether we have the point below the lower bound or above the upper bound. And this alpha basically corresponds to the coverage. So 101 minus alpha, this is the coverage that we have, right? So if you have, let's say, 90% coverage, so it means 1 minus 10, so alpha would be 0.1 in this case. Okay, so this is something called Winkler score. And of course, in both point forecast and Winkler score, lower is better. So we are interested in a method that gives us lower scores in both point forecast and then prediction intervals as well. All right. And then what if we are interested in the quantiles? So if you are interested in the quantiles, you can also calculate the quantile score. This is quite similar to the concept of prediction interval. So in this case, we have YT, which is the actual, and then we have the FPT, which is the quantile, corresponding to a percentage that I mentioned. 90% quantile, 95%, 99, 80% quantile. And depending on whether that is below or above the quantile, we also calculate a score like that. So, and this P also is corresponding to that percentage. So in some textbook, actually, they multiply this by 2, because let's say if you have a P of 50%, right? So 50% and 50% here both become actually 1. And this is a nice property because the score will be simply the absolute value, the difference between the quantile and the actual. So I want just to mention one important thing here as well. There is a relationship between the prediction interval and quantiles. Let's say if you have a prediction interval like this, and you say this prediction interval is 80%. Okay, so if the prediction interval is 80%, it means there is a chance 10% lies here, and then 10% lies there as well, and that would make it 100% total coverage. Okay, so this is the 80% prediction interval. Now, if I take that one as a quantile, that would be everything below that line. And this will make it 80% plus 10%, 90%. So as you can see, there is a relationship between prediction interval coverage and quantiles. So 80% prediction interval coverage corresponds to the 90% quantile because it has everything below that. So there is a relationship. If you want, you can draw things and you will understand that relationship yourself as well. Okay, so there is one last thing that I mentioned, and then we can have a quick, maybe 10-15 minutes break. So what if I'm interested in the not just one quantile, which is related to a prediction interval, but many quantiles? And this is where we talk about continuous rank probability score. So continuous rank probability score gives us a score for the entire distribution that we visualized, right? And this is possibly something that we always interested in. So if you want what actually continuous rank probability score measures, this visualization helps you to understand that. So in the x-axis, you have all possible outcomes, because remember, in the distribution, we have a PDF. Okay, we have a PDF for distribution. So here we have all possible outcomes. So this is exactly what we see here in x-axis. So now, instead of having the PDF, I'm interested in the CDF, the cumulative distribution function, right? So what we do then is we go and calculate that for all models. So because for each model we get the PDF, the distribution, we can calculate the CDF. And then we draw that CDF like this line. And then what is this vertical line here is the actual outcome. So remember, we forecast, let's say, for the next months. At the end of the next month, I know the actual value, right? So if I know the actual value, the probability of having other outcomes would be actually 0, because I know that it wouldn't happen. If it happens, then the probability becomes 1, and that's what we see here. And because I know it, so that I wouldn't get any chance to other probabilities. So what in CRPS, what we are interested in CRPS is the area under this curve. So we calculate this CDF for each model, and we want to see how close this CDF is to the actual vertical line. So basically, let's say if you have another method that has a CDF that is like that, this should be just a line really that goes here. So my mouse doesn't help. So do you see this one is closer to the actual? So the CDF, this is closer. This area is smaller comparing to the yellow side. Okay, so this area is smaller than the... Okay, so this area that I highlighted is smaller than the area of yellow that corresponds to that red line. So that means the method corresponding to the blue line has a lower CRPS comparing to the other one. So we do this for each period and each model, of course. And this is common for the point forecast accuracy and Winkler as well. We do it for each model and each period. And we do it for the entire horizons. And at the end, we take an average of everything if you want to report a forecast accuracy error measure. Okay. So. All right, I think that's it. So when we are back, we can start looking at some examples here. So I think we are a bit beyond the schedule. Can we be back at 9:50, everybody? If you want to take a tea, coffee, or water, you can still drink it as I go through things. Okay, so I'll see you in 10 minutes. So there was something I wanted to do that I couldn't do it while I was doing it. But anyway, during the break, I think the problem was this part that didn't match, actually. Anyway, so if you want to get something like this, so it is possible to do it. So you have the actual, the fitted value to the actual, and then you can also get the forecast. And there is a code here that you can use, and you'll get a copy of this later. You can do it as well. So this is what we did yesterday. So if you just do that, you will get the forecast, the visualization of the forecast. And then if you, I think, let me see if I can add this earlier. And if I do that now, add one auto layer to this, I will get the actuals. And if I get the fitted values here, actually, that's exactly what I want. Okay, so we can do that if you like here. Or what if I get rid of that? And you can do this. Okay, so you just need to add 2 geom lines to this. And then you need also to provide the data that you use for those geom lines here, because this is different from the data that we use to create a ggplot. So that's why we need to provide that here. And then I want to filter index just to show a part of it, because if I don't do it, the historical data would be long. And so that's why I provide that data here. And then I need to make sure that these are inside aesthetic as well. I provide this color just to see those 2 names there, right? So the fitted and the data. If you ignore them like that, and then you run, you see that you don't see that legend. So it's up to you whether you want to have that or not. So I think this is really cool and helpful. So you can get an idea of how good the model that you're using is fitting the data, and then later you can also get a forecast. And actually, we can now do something where when I create the test, I can also visualize the test set there as well. So that is also possible. So that was one thing that I wanted to mention. And then I think now we can move on to talk about what we have just covered. Okay. So we learned how to produce the forecast and how to fit the model. Now we can go and look at this accuracy part. So the accuracy part starts with always splitting the data. So I will go and actually grab my data. So the first thing I want to do, I want to split it into train and test. And you can do it in many different ways. So I want to try use filter index because that's something that we have been using. But the first thing I want to do is I want to define a new variable called forecast horizon. And this is something you can do as well. So I take my testable, and then I say filter index. And then inside this, I want to say, well, go actually to the last date that we see here in this data. So if you go to the max of quarter, it means it goes to the last date, right? And then I want this to come back, this horizon, right? So basically what I'm trying to get is, I want to, because my forecast horizon is 4, I want just to get that 4 observations, 1, 2, 3, and then 4. Okay, so I go to the max would be this. So it would be quarter 4, and I want to come back 1, 2, 3 to get this one. So if I just put forecast horizon, it wouldn't work because it will go here. I need to see +1, then to go back to here. So I just put forecast horizon, it will come back 1, 2, 3, 4, and 5. Actually, it comes back to here because it starts from here. I say 1 back, 2 back, 3 back, and 4 back. But I want to go and to the next one to start counting 4 and cover all this. So that's why I need to +1 here. You remember filter index needs a character. So if you do that, you need to make it a character first. Okay, so this needs to be inside the character. So, okay, this is the character, and I say from this period until the end. So if you do that, there's a number of parentheses, sometimes could be tricky. So here I get actually this. This I think needs to be this as well, maybe. Yeah. Okay, so this is the first thing that you do. And I actually deliberately did it like that because it could be automatic. You can now replace it with your own data and you can do it quickly. So if you do that, that would be my test set. And if you want to get exactly something similar to that, again, you can do it in many different ways, but I want just to use filter index. So this time, I want to go from the beginning of my time series until this date. So I don't need actually the +1 now. And then, sorry, this should be the train now. Okay, so I take the max of this and then minus forecast horizon. And then that will close this. All right, so that's, I think, what we need. This time I go from the beginning until that date, so I don't need that part. And then now I have my train. Okay, so my train data, it goes until quarter 4 of 2016. And then my test data is quarter 1 of 2017, right? So that's test, and that is train. So my splitting is correct as well. I did actually check that. That's the first thing you do. You split into train and test. What is the rest? It is extremely easy because I just repeat exactly what I had here. So I copy, paste. I just use one model to make it a bit quicker, but you can include all models if you like. It doesn't make any difference. It is going to be exactly the same, or just let's keep them, I think. Hopefully they're not too, the running time wouldn't be too long. So I keep all of them. But remember now I have a new data that I need to use. It is not ours tourism, it's the train. So I pass the train to these models and I run. What I need to do to produce the forecast? Well, it is the same. I just take that fit and then pass it to horizon. Just to be consistent, I don't use 4, I just use the variable I defined there. And this gives me the forecast. So if you look at the fit, this is the Mabel, right? You're familiar with it. And this is the forecast table. Now, the next question then is, and here I don't talk about residuals yet. I talk about residuals at the end. Here I talk about how we evaluate the forecast accuracy. So the forecast accuracy could be evaluated using a function called accuracy. As simple as that. Accuracy is the function that we need to use. Okay, now how I use this function? I take my fable, which is the forecast table. I pass it to accuracy. And then inside this, I provide all the data that I have before splitting into train and test. And I put a comma here. And I encourage you also to go and look at the accuracy function here. So in Fable, you should get some information about the functions that we have in accuracy, different aspects of these functions, etc. All right. So you can do that. Now, one important thing that I want to highlight here is you can provide an argument called measures. And this measures take a list. And then here I can have point accuracy measures, comma, prediction, prediction accuracy measures, hopefully it is correct, right? And then you can also include the distribution, if you like, there. And then for the distribution, you put a comma, and it should be distribution accuracy measure. And then let's put this in a new name called FCT accuracy. And then run. I think I suspected that one wouldn't be the one I want. I think it is called not interval. Should be fine. Yeah. So if you run that, and then you check what we see here, we get a summary of all this. Of course, we don't need maybe everything here. You can go, if you like, to select, for instance, that model. This is actually what we're interested in. And then let's have MAE, R, MSE, Winkler, and then CRPS. Okay, so now for the time series that we have, which is the total tourism in Australia, and the list of forecasting models that we have here, we calculated the forecast accuracy, point forecast accuracy, prediction interval, and the entire distributions. Of course, we are interested in the method that gives us the lowest score in all of this. So if you look at the CRPS, for instance, let's see, the lowest it seems like is the automatic ARIMA. It gives us, if you are interested in the entire distribution, that would be probably the one that you go for. If you are interested in the prediction intervals, the ARIMA is doing good here as well. When it comes to the point forecast, so I have root mean square error. And if you look at that, actually the one that has the lowest error measure in this case is just a simple naive method, which is very interesting. If you look at the CRPS of naive, is not too bad as well. And if you look at the mean absolute error, again, automatic ARIMA and naive, they are close, but naive has the lower score. So if you look at this time series based on what we have calculated, and it is just one sample, this is actually the output. So we are interested in a method that based on a selected measure that gives us the lowest score. So it seems like there are some questions maybe. What happens if provide a digit in the filter index instead of horizon? Nothing happens, but I wanted to be consistent. I wanted here define what is my forecast horizon, and I'm clear that is that, and every time I refer to forecast horizon, I use that value. So if you want here, you can use 4, and that would work as well. But I wanted to write it in a way that you could reuse it easily later. Yes, yes. All codes, again, all materials will be in the website. Everything that we do, like live coding, will be available. Everything else that we talk about, it is in the website. Okay, so this is something we call a simple train and test. And based on this, it tells me basically naive is quite good because even CRPS is quite close to this. But if you care about the entire distribution, then ARIMA and ETS, they're actually better than others. So average is not doing good at all. Seasonal naive is not doing good at all. Regression not, but naive is good. Now, can you tell me, is this a good idea? Just fitting a model on the data and test it in one horizon that we are going to forecast. Do you think this is a good idea or not? Okay. Is it Michael? Michael have a strong opinion on this? Not at all. Which is exactly what I like. It would be really good if you can elaborate on that. Why not at all? Why testing on several horizons would be better? Maybe you can reflect on this for a couple of seconds. Yeah, but this is exactly what we did. So we tested the data and the model. Okay, so here we tested our data and in our performance on a new data. Okay, I tested and untested. So basically here I provide all the data, but this is for calculating accuracy. When I fit the data, the model to the data, I just used train. I didn't use any data here in the test. So the model just used the train data and I will test them only on the test set. So what you say here, I have already done it. Well, if I make a decision based on only one forecast horizon, this is too risky. I'm not very confident actually about recommending this method because if I do forecasting, which is the case in many cases, in many organizations and situations, you forecast this many times. It's not just one time that you forecast. So I want to make sure the model that I recommend to people to use has been tested in multiple different samples, which means multiple different horizons, which corresponds again to different situations. So that's the reason I don't want just to rely on this. I want to do something else that captures that for me. And that is the concept behind time series cross-validation. Okay? So we started with a simple test and a train. And then based on this, we could make a recommendation. But then we stopped here. We said, is it a good idea? Well, the answer is it might not be a good idea, because if you make a decision only based on this one forecast horizon, it is too risky. So I want to try something else. And that is the idea behind time series cross-validation. So let me introduce time series cross-validation, and then we'll see how we can do it. All right. So there are different versions of time series cross-validation, by the way. But what is important is why we need to do time series cross-validation. And this is exactly what we discussed. So we have past data and we have the future data. So what we did so far, we said, okay, let's take a past data, split it into train and test, and the test size is equal to the forecast horizon. We said this is too risky, and I need to have more forecast horizons to test on. So we could do something like this if you like. If you have a lot of data, you can still leave out one part equal to the forecast horizon. If you want, you can actually visualize that at the end to see, does this looks good visually? But you don't actually make decisions based on that. So this is one version of it. When you say, I have my past data, initially I split it into train and test, and then I take that train and I do cross-validation with that. But you could do also cross-validation with the entire data. So not leaving out that part. So in the cross-validation, the blue line here shows the train and the red line shows the test. So I have the initial time series. I will get one initial blue line that you see here. I mean, blue points. I call it, this is my initial time series. And I use this to forecast the next period. And I hide the rest of them, the gray ones. And then what I do next, I reveal what I had here and I include it in the previous time series, and I get the second one. And I forecast for the next period. This is one step ahead forecast. And I now, to create the next one, I reveal the actual value of this. I include it in the previous one, and then I get the third time series, and I forecast for the next period. I keep doing this. Okay? I keep adding the observations to the previous one, and as you can see, now I have multiple time series basically created from the original time series. We call each time series here one ID. So later in Fable, we see that ID for that. Okay, so there are three main functions that we need actually to remember, or the way we create those rolling windows is stretch testable, slide testable, and tile testable. We use a stretch testable today. In the apply exercise, you need actually to use slide testable as well. So these are two functions that you need to remember how we use them to create time series cross validations. I think I want actually to show you this in Excel. I think it would be very easy to understand it. So let's say you have a time series like this. So how we implement time series cross-validation? We said initially we leave out 4 periods, but we say this is too risky. Let's do more. Now you may ask, how many more? Well, this depends on, so I hide them. This depends on length of the time series, but as a rule of thumb, people say 20% of observations for this, 80% for the rest. So whatever length that you have, how many, for instance, here I have 26. So 20% of 26 will go here, 80% will go here, or 70% goes here, 30% goes here. Okay. So that's the first thing that we do. So now this part includes more than 4 periods, because my forecast horizon is 4. This is now more than 4. And this is exactly what I want. Now I'm trying to show you how we create time series cross-validation. So in time series cross-validation, this is exactly what it happens. We take this, we bring it here. And then we create an ID. It could be at the beginning or the end of this column, it doesn't matter. And I say this is my first ID. This is the first time series that I have from here. And then actually what happens is I treat this like a testable now. I fit my models on this, and then I go and produce the forecast with this. And actually I will get something similar in my fable or forecast table. I will get this and then that mean, and then possibly that model. Okay, so again, I have 1, 2, 3, 4, because this is what I have, 1, 2, 3, 4. That would be my index. And then this would be the name of the method, doesn't matter. And then this would be that distribution that you see normal, I don't know, 200, 100, whatever. And then this would be the point forecast. Okay, so what happens is I created one ID and I forecast for it. Now, what is the next step? I reveal one observation. I include it in what I had previously, and this becomes my ID2. Sorry, this should be just one, not this should be ID1, and this should be ID2. Okay. Now I repeat exactly the same thing for ID2 here as well. Okay, so just to avoid confusion, I created one ID corresponding forecast. I added one to the previous one. I create ID2. I will go and create the corresponding forecast. Okay. And actually, we keep doing this. We keep revealing new information or new periods added to the previous one. And then this would become ID3. And then I keep revealing this ID4, ID5, and then I have to stop here. Why? Because if you look at here, I have 1, 2, 3, and 4 observations left. So if I'm here in ID5 and I forecast for next period, because my horizon is 4, 1, 2, 3, and 4. So I forecast for 4 horizon, and it is fine. But if I keep revealing, now here I have to take the train and forecast for 1, 2, 3, and 4 periods. But I don't have any actual here to calculate the errors and then accuracy measures and so on. So that is why I have to stop creating this different IDs, we call them also rolling origins. So if you came across time series rolling origin, they are the same thing. So if each ID, we call it an origin as well. So I have to stop here. So when I stop creating these IDs, when the number of periods left equals to the forecast horizon. And this is where I say I stop here. Okay, so I take my initial data, I split it into train and test. This time, the size of test is more than forecast horizon. Typically 20%, 30% of the size of my data. Following that, I create different IDs, and then I apply or fit each model on each ID, and then I forecast for each ID as well. Can I double check if this is clear with everybody? If you have questions, you can put it in the, because there was, I saw questions. If you ask questions, please put them in the Q&A, because I can look at the Q&A easier, and I can double check later as well if I missed anything. So can I double check if this process is clear to everybody? If it is not clear, well, let me know. Maybe I can, because it is important to understand actually how this works. Can I double check with everybody? Tell me, what do you think? Is it clear? Is not clear? Put something in the chat. Okay, thank you, Savas. I just want to make sure that everybody actually understands what we're talking about when it comes to time series cross-validation. Okay, clear. Okay, wonderful. So, okay, so there is a request to repeat on cross-validation very quickly. So, you have a concept of cross-validation in machine learning as well. The idea is the same, but it is a slightly different. Here, it is time series cross-validation. So we always start with splitting data into two parts, and then we implement time series cross-validation to create different IDs. I explained how we do it here. We start with the initial. Let's go back to the one. We start with the initial split, okay? The size of this and this. And then this would be my initial ID. And I call it ID1. All right, can you note something here, please? The size of this, for instance, here I have count 18. This is something that we use later in R. We call it init, .init for initial. You will see an argument like that. This will correspond to this one. What is the size of the first ID that I create? So that's one thing. Now, what happens next step? Well, I have to add something to the previous one. And this is also an argument called .step equal in Tessable that we use later. It's a function from Tessable called stretch Tessable. So that step tells me how many observations I include or add to the previous one. So if you add each time one, so I reveal one, I add it to previous one, and that becomes my ID2. And then now I have the second ID, and my step was 1 as well. I just added 1. You could add step 7. So if you do step 7, it is a slightly different. So, and you keep doing this until when right? You have only 4 periods or observations left because my forecast horizon is 4 period, and you stop producing different IDs there. And now what happens? You apply each model on each ID, and you produce the forecast for each ID. Okay, so each ID has 4 horizons because this quarterly horizon was 4, so it means 4 quarters. All right. Now, if a step is more, this is what happens. Let's say you start with ID 1, and you tell me, I want to include, my data step is 2. Actually, this data step could also relate to how often you produce a forecast, which is about frequency of producing the forecast. So you may tell, I want to include 3. So what happens is, this is your first ID. The next, you go and say 1, 2, and 3. And then you reveal this. And you add this 3 to the previous one. And this would be your second ID. So next time, again, you do the same thing. And you do this until you have also reached the limit of the number of observations left equal to forecast horizon. Okay, now I think I want to go to R and show you an example. Okay, time series cross-validation. Surprisingly, it's so similar to what we have seen here. So let's see what is the difference. So I start with defining the forecast horizon, which is 4. I want also to define another parameter. And we call it percentage of the test set. Percentage test. I put 20% here. You can put 30% if you want, and anything that you think it is relevant. And now I want to also split it into that first train and test part that we had initially. So to do that, I take my data, which is my testable here, 1 time series, but it is similar to many time series. You do exactly the same thing. And then the first thing I do, I filter. And then, of course, I want to use filter index. As I said, you can actually do it in many different ways. So this time, I will go and basically take the tourism, house tourism data, and then quarter. And if you take the max of this is similar to what we have done before. If I just select that, you see you will get the last quarter basically in the data. All right, so this is the first thing that I do. And I want this time to go and calculate the percentage of what I have here, the test set. Okay, maybe I'll just do it here to show you. So the percentage of the test, which is the variable I defined here, I defined both of them. I have to run them as well. So I multiply this by length of the same data set that I have here. And then, of course, I need the quarter here. So if I take the length of that, this tells me what is the length. So it means how many I have there. So that's one thing that I need to do. And I actually need to use another function here because sometimes I want to write this code that works for many time series as well. So if you just do that and you have many time series, that wouldn't be correct. So I need to actually take the unique of this. So because if I have many time series, the index repeats. okay, but I want just one of them, so I take the unique part of that. So this sounds a bit complicated, but you can also go through it step by step and produce it. Okay, so I think if I do that, then I will get also something like that. So the percentage of this, okay, and I need also, if it is, sometimes it might not be a round number, so you can also round it to make sure that it is going to work actually for everything. So you can put a function called round here. In this case, it is round, but sometimes if it is not, then you can add that as well. So if you do that, then it tells me how many observations I can put in the test set from that, or how many periods I can put in the test set. So again, similar to what we did actually previously, I need to add one period because I say come back 24 and then go to the beginning of the next one. So this is something I need also to deal with. And remember, because I'm going to use the filter index, right? I need to go and say, so this is the max, it means goes to the last element minus this part, which is a bit long, but this is exactly what gives us.
There's a bracket. There's a bracket missing just there.
Should be here. Let me check. It should be
just before the minus, because that's where they.
Yeah, but this should be here actually. Or
okay,
should be maybe here. I have to double check this. Yeah, so it's a bit tricky.
It is in that function of max. After max, Australian tourism, then before the minus sign, I think. There.
No, it's not there. It shouldn't be there because I need to put an as that character, right? Okay. I need to make this a character. This is similar to what we did before. So I need to actually make this as a character and say from this date to the end, something like that. So let's see if this works. Okay, so that gives me actually my my test part. So as you can see, I have 24. So 14 plus 10, 24, right? So this will be one part. And this actually now it works for many time series as well. And that's why I wrote it in this way. As I said, you can always write or find ways to do things differently. So the second thing is now I want to go and say, I want now something from the beginning until this, but this time I just need to get rid of that one that I had. Okay, now maybe I have, so here I don't need actually those parentheses. Parentheses could be always tricky. Okay, so that works. Sorry, that should actually, I should name this now train. Okay, so if again I go and check the train and then test. So my train goes up to Q4 of 2011. And something is actually not right here. So let me see. So this is my test. Just run it again. And then this is my train. So my test set should be 24, which is correct now. And then my train. So this goes from 1998 to Q4 of 2011. And then my test set starts from Q1 in 2012, right? So they match, and this is exactly what I wanted. So this is the first part. Now, what is the next part? The next part, we have to use a function called stretch testable to do the calculation that we need. So To do that, I take my data, and then I also do a filter index here. And this time I do this filter index for the reason I mentioned, because I have to go and do this process until when the number of observations left equals to the forecast horizon and stop producing IDs there. So for that reason, I need actually to do this filter index here as well. So I said point, it means from the beginning until now. I have to provide also the same sort of a character that tells me where I have to stop. And this is going to be the max of the data. And I look at the quarter, extract the quarter part of it. And this time I just simply grab the forecast horizon. Just make sure that I get this right in terms of parentheses, and then that should be fine. Okay, so I have my dot until, so from the beginning until as that character, and this would be the max of the data, and then the quarter, that is fine, minus forecast horizon. Brilliant. And then I pass this to the function called a stretch testable. So you remember I mentioned there are two arguments here, dot init and then dot step. So what is dot init? Well, the dot init is actually the length of the index in my train part. And again, I write it in a way that would work with any sort of number of time series. Okay, so I take the length and then I take the unique part of the quarters. That should work. If I look at this, this is telling me we have 56 basically there. And then what is that step? Well, let's leave it to 1 here. So it means every quarter I generate a forecast for next 4 quarters. And then let's call this TSCV for time series cross validation tourism. And then run. So if I run, and if I look at this now, you see that I have an ID. So this is a testable, it's a quarterly testable, and I have 21 different IDs. It means now I'm going to evaluate the forecast in 21 different forecast horizons. I mean 21 different 4-step ahead forecasts. That's what I mean. So different samples, different situations. So this is exactly like what I showed you in the Excel file. So what is next? Extremely easy. Whatever we did here, I just copy it because it's exactly the same. And then paste it here. So what do I need to do here? I need to make sure I use the right data. The data that I need here is this one because it includes all the IDs. And remember I mentioned we use the models, we fit them into each ID, and then you will get the fitting. Look, it takes time now. I mean, I don't know how long it would be, but because we do this multiple times, 21 IDs, it takes a bit of time. Now, if you look at this, it is slightly different from what we have seen before, because we had initially 1 time series, but because we do time series cross-validation, we get 21 IDs, and each ID, we treat it as a time series. So we will get 21 rows as well now. And remember, model table, each row is 1 time series, each column is 1 method. How we produce the forecast? Well, I take that fit, pass it to forecast, and then forecast horizon. So it is pretty straightforward. And then if I look at the forecast table, it is similar to what we had before. right? So nothing different. It just tells me that the combination of different models and different IDs are the keys, and in total we have 126 of them. So when it comes to forecast evaluation, again, I take my forecast table, fable, pass it to accuracy function. Inside this, I provide all data. And this is the beauty of using the accuracy function, because you don't need to go and match IDs and indexes with the train and test. This function will does this automatically. So it will match each ID from the train to each ID in the test, then calculate the accuracy. So if I run this, and if I look at this, we will see how results are different from what we have seen before. So this is now quite interesting because it changed actually. So the result we have seen before was naive as the best method. So naive was the most accurate one. But if you look at the result now, almost, yeah, for all measures, doesn't matter if you look at the MAE, RMSE, Winkler, or CRPS, it tells us the automatic ARIMA is the most accurate one. But if you just rely on one single test set, we saw that it told us, no, it is not the case actually. It is naive. But I told you, I'm not confident. I can't recommend that to people because it has been tested in only one situation. But now I tested it in over 21 different situations. So, and that means around 5 years of data, basically. So I have tested it in over 5 years, and this is the result overall. And this is, remember, this is a total average. So it means the errors have been calculated for each period over the horizon, and then for each IDs. And then we take the average of all the IDs, the average of accuracy across all IDs. And this is the outcome that we see. So this is what we call an overall accuracy, or the average error measures. And you can go into details of things. If I have time, I show you. If not, in your apply exercise, you have to do two more things when it comes to accuracy. You have to plot accuracy across the forecast horizon. You have to also go into details of accuracy for each ID and create a distribution of the error measures across different IDs. And this is something you will do in the apply. If I have some time, I might be able to do it as well. So this is one important thing that you need to remember in terms of how we do it. We need just the accuracy function that takes the fable as input, and then the data, the entire data that we have, as a second argument. Following that, you provide measures, and here we can include all measures, including point, interval, and distribution. If you want just to include one of them, you can also do it. If you are interested in only in point forecast, then it will just calculate only point forecast. So there is no prediction interval. If you are interested in the prediction interval only, this is what we do, right? So you just look at that, and then it will give you the Winkler score only. And if you are interested in the distributional one, then you just look at the distribution. But it would be good to look at all of them together. That's one thing. So another thing is, if you want to look at, for instance, Winkler score or a quantile of a measure in a different way, it is possible to do it as well. For instance, if I take the, let's say this one. Okay, so I take my fable, I pass it to accuracy, I put the data as a first argument, and I put here a list. So this takes a list, and I say, well, quantile score, this is a name I provide here. So actually, there is a function called quantile score. And if you want, you can go and evaluate the score of each. It's called props. Let's say if you're interested in the 90% quantile, so you can go and say, can you calculate the quantile score for 90% quantile? And it goes and does it for all methods. So if the quantiles is something that you are interested in, you can use the quantile score to evaluate them separately. You can do the same thing with other accuracy measures as well, by the way. So all of them, they have a function. For instance, if you are interested in the Winkler, so there is a function called Winkler score. Of course, it requires a different argument. So I think it is called level or levels. No, that should be that one. And then it will work like that as well. Maybe I just copy paste it with the previous one, just to make sure it works for both. So I have quantile score, and then here I have props. So if you want to calculate them like that, it is also possible to do it. Is there any question? I know there might be many questions and you have time actually to practice this, but if there is anything not clear here, so let me know, please. I can go through this again. Okay, so there was that question yesterday. You care about how good the forecast is. Well, this is how we evaluate it. So time series cross-validation is the most important aspect of this, and probably is the most robust way to evaluate forecast accuracy, really. So if you have enough data, you need always to consider it. And again, how much data you leave in the test and train, it depends on how long your historical time series is, but as a rule of thumb, as I said, 20%, 30%. Now, for instance, if you work with monthly time series data and you have 6 years of data, well, you can leave out at least 2 years of data for test and then train your model and 4 years of data and test them using time series cross-validation on 2 years of data. Any question, anyone, about how we evaluate forecast accuracy using advanced approaches of time series cross-validation? Okay, so if there is no question, I can probably show you one more thing, but you practice this and apply exercise as well. And but I have time, I can show you that as well. And not necessarily. Again, the choice of error metrics is an important one. So there is no really what is the best or what is the worst forecast accuracy measure. So often you may get a question, what is the best accuracy measure that I have to use? There is no such a thing, really. It depends on what you do. For instance, if you produce a forecast and you care about the point forecast accuracy or the mean of your distribution, you may rely on root mean square error, because actually root mean square error minimizes the mean. And if you have mean absolute error minimizes the median. So if the median of a distribution is what you want to get as a point forecast, so you may use mean absolute error. So as a recommendation, you can include mean absolute error, root mean square error together. So it is good to always look at the accuracy measures from different angles, and each error measure looks at the forecast accuracy from different angles. So it is good to have a couple of them together. But if you have like issues, for instance, such as having zeros in your time series data, intermittent time series, I think there was a question the other day about that. So for instance, you cannot use certain number of measures, like mean absolute percentage error wouldn't be useful here. But also there is the issue of scale dependent, scale independent. You need to be aware of it as well. So if you use a scale dependent measure to evaluate the accuracy across many time series, they have a different scale, then this would be misleading. You shouldn't be doing it. You should use scale independent measures that we have. For instance, here we have MACE. Well, I have to recalculate this. I think it doesn't. Is it MACE? Is it that? Oh, okay. Sorry. Here, instead of, I have to go back to that point accuracy measure. So if let's say you calculate point forecast accuracy measure, and then here you have, for instance, MACE and RMSSE. So if you have the issues of scale in your time series, so you have time series with different scales, you have to use MACE or RMSSE. This is what we recommend. Oh, yeah, absolutely. Let me do that as well, if you like. It's a good thing actually to do. Thank you for that. Let me just include it here. Actually, let me just maybe not this one. Let's just leave it like that. And so I will just add point and then interval. Okay, so the question is, can we add the ensemble method that we discussed? Yeah, let's do that. So we have a combination. This is the name that I give to this. Well, let's take ARIMA. I don't know which one was the most accurate one for this. Was it? Let's combine that with just the ETS. And then ETS. In this case, we divide this by 2 because we have only combination of 2 approaches. So we first do that and then do this and then calculate the accuracy measures. If you look at this, you see actually it does a better job, slightly better. No, not actually. It is here. Sorry, I saw it. I thought it. So the combination is here. Is still not better than that. What if I add something else? Just if I add, for instance, seasonal naive to it. Okay, let's see if that improves anything. All right, so combination. I think it is a bit worse, isn't it? It was better without seasonal naive. The combination was better without seasonal naive. So you can add the different methods. Sometimes could be better. Sometimes it might not actually improve accuracy. So here it seems like the ARIMA is doing well for this one. Okay, so I wanted maybe very briefly to talk about this idea of looking at the error measures across different IDs. This gives you a bit more detailed view of what is going on in terms of accuracy measures in different IDs. So how we do that? Well, again, it is quite similar to what we have done before. So I just take, for instance, this one, and then if we don't provide actually any argument here, like the measures we provided here, then it will just get the point forecast accuracy measures. Okay, so if I do this, you have this, right? So the accuracy measures across all IDs. So this is the total average. So what if I want to get the accuracy measures for each model and each ID? It makes sense because models are different. So first I need to do that by model and then by ID. So there is an argument inside the accuracy measures that you can use, and this argument is called by. So here I need to provide a vector, and the vector should include the columns of that model and also that ID. As simple as that. So if you run this and you check, now you see you have a bit more detailed view of accuracy measures across different IDs and for different models, right? And if you want, you can do something with this as well. Sometimes would be interesting to look at the distribution of, I don't know, RMSE, for instance. So let's say you pass this to a ggplot, and then you have an aesthetic of, let's say, RMSE. Let's put this in Y. So I want to show the values of RMSE in Y-axis, and then here I put dot model in X-axis. And then I want to add a geom box plot. So if you do that, you can actually see, maybe I will change X and Y, just should be a bit better. Okay, so you can get an idea of the variation of the error metrics, RMSE, across different IDs. And you see actually there is a variation. For some models like ARIMA, they have less variation. There are outliers there, but you can see the variation for the RMSE in average. So of course, we are interested in a model that has less variation maybe. So that means it is reliable across different IDs, rather than something that has a large variation. You can also rank this based on median, for instance, if you like. So I could do FCT reorder. Is it FC? I think I need library tidyverse, or maybe it is already, not sure actually what is library tidyverse. So let me check. Yeah, I wanted to reorder those box plots based on the order. So I wanted to order the methods based on the value of the root mean square error. should look better. So that's actually more insightful because you can see the variation, how it increases from regression to average, naive, and so on. So this sometimes is helpful because it can give you a more detailed view of the error measure. Okay. So far we have looked at the forecast part, because remember when we, let me find the plot. I think it was here, right? When we did this, so we said there are two main things that we are interested in terms of the models that we have used. So first of all, how well these models fit the data. This is the part that we are interested in. And also how well these models forecast. And basically the how well question is related to the evaluating forecast accuracy. And this is what we did with the simple train and test, but also with time series cross-validation. So we have covered actually that part. Now, what can we do with this part, with the how well this method fits the data? So let me go back to my slides, and then I think I need to open it maybe. It's not open. Oh, it is open already. Okay, I think this is the sort of thing we had covered. So this is about residual diagnostic, basically. So the fitting part is about residual diagnostic. We have already discussed what are the challenges of just focusing on a good fit. So we discuss about the idea of overfitting and also the trade-off between variance and bias there. So the overfitting is not a good thing, even if it is possible to get 100% fit, but possibly it would be terrible when it comes to forecasting the future. But we can do some interesting stuff with the fitting part as well. In particular, we are interested in the residuals. So there are certain assumptions that we can check with the residuals, and they help us to understand whether the model performs well in certain aspect or not. So we have already discussed what a residual is the difference between what we observed and the estimation. So when it comes to the residual diagnostic, we are interested in checking some assumptions. First of all, we want our residual to be uncorrelated. So that means if you go and plot the residuals, they should look like random, or what we cover in day 2, white noise. So if you look at the residuals and they have patterns, or you identify some systematic patterns in the residuals, it means something is left in the residual, because residuals are leftovers. But this is not a good thing, because if something is left, it means we could do something interesting with it, but we didn't, right? So an idea would be probably go and see whether you can find a better model, or maybe include something, I don't know, a term, a predictor that could help you to improve the modeling. So that's one thing that we look at the residuals. They should have also a mean 0, because if they are not, then the forecasts are biased. This is something we can fix it easily by adding or subtracting a constant value if they are not biased. But the other one is slightly more complicated. There are also other assumptions, of course, about having a constant variance and also having residuals following a normal distribution. Because remember, the forecast distribution that we discussed, but also the prediction intervals are constructed based on this assumption. If they are not valid, then we will have troubles there as well. So here is an example of from a GAFA stock data set. We look at the closing price of Facebook. And again, this is from financial market. You may guess what sort of methods would be useful here. So we can do some I mean, we can do some manipulation here because we don't actually have a index that is helpful here because there are gaps between them. So we need to calculate the trading days to get that and then update the index. And then we do the rest of the modeling. We look at the fitting, and then actually there are two type of leftovers here. One is called .RISD, another one is called .INOV. Most of the time they are actually the same. But if you do a transformation before fitting the model and forecasting, or for certain number of models, for instance, like multiplicative seasonality, we see an exponential smoothing, these values would be different. So in that case, for instance, I mean, just very quickly, I can draw something here. Let's say if you do a log transformation of your variable, so this, let's say if you call it W, so the residual .RISD in this case would be YT minus Y hat T. And then if you do a transformation, then .INOV would be actually something that we calculate like that. Okay, so the difference between the .INOV and .RISD comes from that. So if you have transformation for certain type of models, then this would be different. Otherwise, they are the same. We prefer to use this one for the residual diagnostic and not .RISD. So make a habit of using that one, even if they are similar. All right, so let's close this. Yeah. All right. So we can add the fitting to the data. As you can see, it's quite a good fit, very close to the actuals. And this is naive. We see how naive works. Just look at the previous one, right? If you look at the residuals, well, here they are the same, so you could use that enough. Well, you see actually there are some extremes. They are it seems like something is left that could be captured, but also seems like the variation here is a bit higher than the other parts. So that could cause issues when it comes to checking the assumptions of residuals. If you look at the histogram of residuals to check the normality, you actually see it's not quite normal, right? So you have some values even here, some values here, some values here. So one thing that you can do is actually you can look at the ACF of residuals. So we discussed about autocorrelation functions. We can use them with the original time series, but they're very helpful when it comes also to check whether the residuals are significant or not. So in this case, we want our residuals legs of autocorrelation all to be inside these intervals. If they are inside intervals, it means there is no significant information left here. So yeah, this is something I think we mentioned. There is one function that you can also use where you can get the time plot, the ACF plot, and the histogram all together. And this is GGTS residuals. So if you take your Mabel and you pass it to this function, you automatically get this one. You can also do some formal test if you like. So if you don't want to rely on the plots that we shared previously, and you want to do a statistical test to see whether there is any significant information left in the residual or not, you can also do this. So there are different tests for this as well. One is Leung-Box test. You can also use the features function to do it, right? So here the idea is basically to take the correlation that we calculated for different legs, that's our k-means here. And then we square it and we take a sum of it multiplied by t, which is the total number of observations, and then k, which is the maximum number of legs. Then here we have also, of course, another part of the test. So the function that I mentioned is this, features. So we take the fit, we pass it to the augment function, and then pass it to features. You can put .visit or .inof. In this case, they are the same. And then here you can say, what is the test that I want to use? And then here you provide the number of legs, actually. Right, so if you do that, it will give you some information. It is a table, and it gives you a p-value as well. And this p-value, well, the sort of benchmark for this is going to be 0.05. So it is, I think I can write 0.05. So you compare the p-value with this. So smaller than or bigger than that. And based on that, you can reject or not the null hypothesis, which means the residuals, they are correlated or not. Okay, so I think when it comes to residuals, it's a good practice to do it, but what we care about really is forecast accuracy evaluation. So my recommendation is always do the time series cross-validation if you can, identify the best method, and then you can go and check the residual diagnostic with the most accurate method that we identified to see whether anything is left there. Of course, you can do residual diagnostic with every single model as well. So it is not just for the best model, you can do it with all others to understand the behavior of residuals. All right, so an overall recap. When it comes to a project in terms of data analysis, and here we talk about forecasting, there are a certain number of steps that we follow. We start with the temporal data. It means you have a data set like Excel CSV with column and rows, and at least there is a column in that data about time. So it could be date time or date, months and year, quarter and year, and so on. You import the data into R, and then you, of course, check certain aspects of the data like quality, duplications, gaps. You create a testable. Why we do a testable? Because testable has many functionalities that could help us when it comes to temporal data. It is very strong in that aspect. It can handle time series data really well, not only one, but many of them. But also all the functions that we use later, including time series graphics, fitting models, producing forecasts, and then accuracy calculation, all of them, somehow they require different data structures, but when it comes to model fitting and time series graphic, they need to be testable. Okay, so that's another reason, because the functions that we use later, they depend on this structure. So we have to make them testable. That's a very important point. Following that, we go and visualize our data. We want to see whether there is any systematic pattern that can be used to produce a good forecast. Remember, if there is no systematic information, it is unlikely that you can do any good when it comes to producing a reliable and good forecast for informing decision making. One important thing is, remember, domain knowledge is very important here. It helps you to identify driving factors. It helps you to understand your data and building a forecasting model that is reliable. So following that, you come and split your data into train and test, and you create time series cross-validation, so different IDs, that's what we discuss, or different rolling origins. And then you model each method that you have in your toolbox and each ID, and produce a forecast for them, evaluate the forecast accuracy, and it decide which method is the best. Once you decide which method is the best, actually you take that model and then fit it on the entire data that you have, and then produce the forecast for the real future. If you have a real-time data sets, I would say. You can also check the residuals of any model or the best model that you have identified through the time series cross-validation forecast accuracy evaluation. And I think that would be probably the sort of steps that you need to go through when it comes to looking at different forecasting projects. Well, there is no key in your data set, so it is completely fine. So one important thing is, in a data set, in any data set that you work with, index is a must. So you must have index. I have worked with data sets where I had only arrival time. So arrival time and each row was like a patient. Arrival time was my index. In that case, I had to do some more transformation to go and calculate my measurement because I didn't have it. I had only the arrival time. So arrival time was my index. So index is a must. You have to always have it. Measurement, in the example I provided, arrival time, even if I didn't have it, I calculated it with some manipulation. But key is normal. So if you don't have any key, well, you don't have it. You just have one time series that is about crude oil price. Whatever I thought, maybe it is the which oil price and think is that, I don't know, but it is only one time series. So there is no problem with that. So if you don't have any character variable in your data that can be used to identify separate time series, then there is no, you don't have the key basically. For instance, let's say if you had oil production here as a measurement instead of oil price, then you could have a key called country. So you could actually have a time series of oil production for each country, for instance. That could be a key there. But in your example, there is no key, and it is fine. Wonderful. I think we're almost on time. I will stop sharing. Well done, everybody, and welcome, Mitch. I think we had like 5 intense days, I think, for most of you, and I completely understand. But I really appreciate all of you being here, and I really hope that you find it helpful. And I think for most of you could be the beginning of a really nice learning journey. So you can start with this training. We have materials that is online and available. The Slack channel could be still there. You can ask questions. We try to be responsive there as well. And you have also the free online books. You can always have them as reference and go back to them. So I think you have almost everything you need really to start doing forecasting and using forecasting, hopefully, for practice. One thing that we could do, and Mitch can also say maybe something about the project. Maybe we can take a photo. What do you think? If we could get people's, if you can turn on your camera, it would be nice to take a photo. I don't think we can put everybody here.
You want to take a photo, group photo?
Yeah, that would be nice. Okay, we're getting people. It is great to see faces now. I know some people here, but
we don't often get to see faces, so it's really nice.
It is really nice. Yeah, it makes a difference because it is hard when there is no face. Sometimes you're talking, you don't know if someone is there, is listening, and when you see faces, it's better, I think.
I also feel like you get to know us so well. You see us all the time.
Yeah, all the
It's nice
time.
to get to know you a little bit more too.
Wonderful. Okay, so how should I take a photo here? I have never done this before. Well, let me first actually